General relativity, step by step. We've derived these nice equations here for tidal acceleration in the Newtonian case, and the tidal acceleration governs my stretching and squashing of a small sphere as it falls into a black hole, I guess. Okay, so we need to translate that or come up with something similar that works in the Newtonian, that works in the Einsteinian case. So what I'm going to do is set up some coordinates. There's space and there's time, and I've got a world line here, x alpha, let's say, indexed by proper time tau, as it cruises along some geodesic. And I've got another equation here. This one here is, I'm going to call it x bar alpha of tau, and that's going to equal x alpha of tau plus n alpha of tau, I guess. So n is the separation vector. N equals the separation vector. Okay, well these are my world lines of my particles, and now I need to write down the geodesic equations for those world lines. Okay, well let's just write them out. We've got d2 x alpha by d tau squared plus Christoffel symbol alpha mu nu, and I'm going to leave a strategic gap here, dx mu by d tau, dx nu by d tau, summed over mu and nu, and that equals 0. That's the geodesic equation for this particle here. Now what I'm going to do is to write out the geodesic equation for the barred particle, d tau squared, plus the Christoffel symbol. All the indices are the same. However, because we're at a different position, we need to evaluate the Christoffel symbol at a different position. You see, this one's evaluated at point x, whereas this one is evaluated, call it x alpha, and this one is evaluated at x alpha plus n alpha. So it's a different thing. It's the Christoffel, the curvature may well be different from one point to another. Times dx bar mu by d tau times dx bar nu by d tau, and that equals 0. So if n is small, we have two neighbouring or close neighbouring geodesics. There they are. And of course, if n is small, that means I can use calculus, and I shall do that on the next screencast. Stop there. Stop.